Hey guys, so this is Archimedes, or the buoyancy problems. So you guys can't see it, but well, it's barely getting cut off. But we have a cubic ice cube, so it's got sides of S by S by S, floating on top. And we want to keep in mind that buoyancy is going to be the density of the water times by gravity times by the displaced volume. Okay, so that's the volume that we find underneath that water line. Okay. And so we have density varying with respect to y, so that's why we're going to make this an integral. Anytime you see that, you're going to want to probably go for a integration. And because this volume has that depth in it. And so what we're going to do is we're going to say, okay, well, the differential, buoyant force, at a particular y is going to be g times by the differential volume. So basically that differential volume is this dy times by, if you look down, so this is top view, it'll be S by S. And that's not going to change. But what's going to change is if we have just this differential dy. And so that's what we're going to do. We're going to say that dv is equal to this S by S, so S squared times by dy. So this is the top, this is the side view. So we get S squared times dy is this dv. And we're going to go all the way actually from 0 to negative s. So let's make it easier on ourselves, negative s. Okay? Rho y times g, s squared times dy. So this is the same as before, rho times g. And then we can plug in the equation I gave you guys for rho. So this is actually a past test question. And so we have the equation that rho is equal to rho naught over 1 plus y lambda times g s squared dy. And again, rho naught, g, and s squared are all constants, so those can come out. And actually, if we multiply through by lambda, so if we remember that this is lambda over lambda, because it's 1, and we add lambda plus y all over lambda, and all over lambda actually means it's on the top, then that's actually what just happened here. And that's why you get lambda plus y instead of this denominator. And you guys don't have to do that, just as right if you don't. But we pull out everything. So we pulled out the g, s squared, and rho naught. So rho naught, g, s squared. And I just, fancied this up with pulling out a lambda and making this lambda plus y. Okay? Over dy. And so when we do that, we're going to go from 0 to negative s. And what we're going to end up getting is this equation. Okay? So that's actually our buoyant force, and that's part of the problem. And then if we go on, let's see. Let me just see if I can rotate this. Okay. Then it turns into a hydrostatic problem, which is exactly what you guys were just learning. The sum of forces in y actually is equal to 0. I should have put a 0 here. And the buoyant force is equal to the weight. And so we're able to solve for the weight. And then you would just divide through by gravity. And I just did this so that I could finish it up. The gravities cancel, and that's your final answer. Okay?